It is indeed a pleasure to be here for Alex's birthday. I guess everyone has their own personal story of how they came to work with Alex. The first time I met Alex was in 1993 at the ITAMP meeting in Aarhus in Denmark. That was soon after I joined Gert Billing as a postdoc in University of Copenhagen. So I had a poster based on my PhD work that was on helium H2 plus scattering using wave packet methods. So I decided to present this as a poster, and my PhD supervisor was also there, Dr. Satyamurthy. Alex came to the poster. I didn't know about Alex at that time, and so we had a brief discussion about the work. And after Alex left, Professor Satyamurthy told me that if you ever want to do another postdoc, he would be a person to contact. So that was in 1993, and about 3 years later, 2.5 years later, when I completed my postdoctoral work with Billing, I was thinking what to do next, and again, so I had this advice my PhD supervisor gave, and I had some opportunity to go back to India at that time, but I wasn't really sure if that is what I wanted to do. So I decided to write to Alex. So I wrote to him asking if he has a postdoc position, so there was no news for about a couple of months. Then I got an email from him inviting me, essentially offering a position. Actually, wording was something like this: the position is for 1 year, but I'm optimistic that I can support you for 3 years. So I was a little concerned, really, what happens if there is no funding after the first year. So I wrote him again, can you make a more firmer commitment that you would be able to support me for 3 years? So Alex said, I'm optimistic that I can support you, but I cannot promise. Now actually I realize that, of course, no one can do that, and I really appreciate Alex for giving me the opportunity to come and work with you and be part of this larger family. So the project Alex suggested at that time was to look at some issues related to hot atoms in the atmosphere, thermalization of energetic atoms, and issues related to nitric oxide formation in the thermosphere. So I started working on that, and considering my background in collisions and reactive scattering, so that was an appropriate topic to begin with. And I had very productive interaction with Vasily on some of those work. And that was also the time around here in Cambridge, as well as at many other places in this country, the beginning of the research on cold molecules, exciting experimental work in creating ultracold molecules using photo association and other techniques. And issues, some of them highlighted earlier this morning, about stability of vibration excited molecules at ultra-cold temperatures through the collisional relaxation. Alex asked me, do we know anything about how quickly these molecules could undergo vibrational relaxation? It might be interesting to calculate some of these processes. So it was really a completely new field. I had, there have been some of these studies at higher temperatures, but really nothing existed up to that point on cold collisions. So that was sort of a diversion for me from some of the things I was doing, but it was an exciting and an interesting diversion. So begin to do both these upper atmospheric work as well as the cold collision work, and so even now at UNLV we continue some of this work. In fact, both directions are being pursued, and so I thank NSF for the continued support of some of this research. So this is a brief overview of what I would like to talk about. I will give highlight some of the initial research that we had on rotational vibrational relaxation of molecules at low temperatures, and also give you some flavor of some of the results on reactive scattering calculations that we did. Mostly we looked at reactions involving energy barriers which proceed via tunneling at low temperatures. We looked at the effect of rotational vibration excitation of the molecule on reactivity at low temperatures, how reactivity is influenced by these factors. And more recently, we are also looking at reactions that do not involve an energy barrier. There have been some studies of several studies of alkali metal atom dimer systems which do not involve energy barrier, but there aren't that many calculations or any calculations on non-alkali metal systems at cold temperatures. And I will also talk about briefly some ongoing work on molecule-molecule collisions that is in collaboration with Roman. So as I mentioned before, the photo association creates molecules in excited vibration levels, and the collisional quenching of these molecules has been an interesting issue, and I guess it still is an interesting topic, and as well as the whether chemical reactions occur and how we can control chemical reactions, which seems to be actually quite exciting in the direction that Roman talked about today. So these are some of the topics that we are pursuing right now, and so this is one of the systems that we looked at. Again, most of these calculations are carried out using the Dalgarno formalism, which Roman has briefly discussed in his talk. So mostly my talk is going to be qualitative, highlighting some of the interesting results that came out of this work. So what is shown here is the vibrational relaxation rate constants for H2 in various vibration levels, V equal to 1 to V equal to 10 in collisions with helium. So up to the point while we were doing the calculations, most of what has been known was around this temperature range where some measured data are available, and our calculations, though I did not include here, the calculations for the V equal to 1 agree quite well with the experiments, but only in this range of temperatures. So this seems to be the typical case of vibrational relaxation rate constants for these van der Waals systems such as helium H2, where the rate constant would decrease with the decrease in temperatures, then begin to show this upturn, and eventually begin to actually attain the Wigner limit. And Alex knew all of this. This is exactly what it should happen. And of course, so it was interesting to see the calculations show the same. And so in this case, the vibrational excitation has some effect on the rate constants. So between V equal to 1 and 10, about 2 orders of magnitude increase. Another system that we looked at is the helium CO. So the choice of some of this system is partly because there have been experiments or calculations at higher temperatures, and these are also relatively simpler system, fairly accurate potential surfaces were available. But there was also the other interest that these systems are of astrophysical interest. So we have been able to do calculations at low temperatures as well as at temperatures relevant to astrophysical environments. And so quite extensive work has been done on these systems, and many of the calculations are subsequently done in collaboration with Phil Stansel and also with Bob Foray. So this is for the helium CO system. We looked at vibrational relaxation in the V equal to 1 vibration level for 2 different initial rotational levels, J equal to 0 and 1. Again, for both initial states, the result is the rate constant is essentially the same at higher temperatures, but there are some substantial differences as the temperature is decreased. The feature here, shown here, essentially comes from the presence of these shape resonances in the cross-section. So when you integrate it over a Boltzmann distribution of relative velocities, then that leads to this local enhancement. And in the case of the V equal to 1, J equal to 1, there is a nearly 2 orders of magnitude increase in the rate constant in the Wigner regime and at this temperature regime. And that appears to be coming from a Fish back resonance that exists very close to the channel opening of the J equal to 1 rotational level of the CO molecule. and the Fishback resonance was not present for the J equal to 0 case. So subtle differences in the interaction potential can cause quite dramatic change in the low temperature values of the rate constants. So then we thought it would be interesting to look at chemical reactions, because there has been quite a lot of talk about superchemistry, possibility of observing chemical reactions at low temperatures. And again, we went back to a system that has been quite well studied at high temperatures, and both experimentally and theoretically in the chemical physics community. So this is after HH2, one of the most widely studied chemical reactions. And it involves a small energy barrier of about 500 Kelvin. So the reaction proceeds via tunneling at low temperatures. It has a fairly large exoergicity, so reaction would populate these excited vibration levels of the HF molecule. And actually the V prime equal to 2 is the most probable vibration level of the product HF molecule, which also is the reason for the HF chemical laser. So that, what we found using a potential surface developed by Stark and Werner, which is considered to be the most accurate potential surface for F plus H2 at that time, it reproduces most of the experimental features of the reaction from the energy threshold to several hundred Kelvin. The rate constant at 0 temperature limit is of the order of 10 to the minus 12 cubic centimeter per second from our calculation, which is comparable to the magnitude of the rate constant at about room temperatures. So that is a fairly large value for a reaction rate constant that occurs in the limit of 0 temperature. The F plus H2 reaction is also, it was referred to a couple of days, in the first day of the meeting, of its importance in HF formation in interstellar medium. So mainly it is due to this reaction that most of the fluorine exists in the form of HF in interstellar medium. The F plus H2 reaction in the tunneling regime occurs by tunneling of the hydrogen atom, which being a light atom is quite probable. Roman talked about the Li plus HF and the electric field induced changes in the reactivity. So an interesting case here is that there is only one channel that is open at low energies. The other channel that involves the transfer hydrogen atom, the LiH plus F, is energetically closed at low energies. So we have only this channel. And this reaction also has small energy barriers. So in fact, the reaction occurs by tunneling of the fluorine atom here. So the calculations, this is again only S-wave scattering in the incident channel for V equal to 0 and V equal to 1. Blue curve is the reactive cross-section as a function of the energy. These oscillations corresponds to resonances in the, due to the decay of LiHF van der Waals complex formed in the entrance channel. And the blue curve here is the reactive cross-section. The red curve is the non-reactive vibrational quenching cross-section. So again, even though it involves tunneling of the heavier fluorine atom, it is the reactive channel that dominates at low energies. Again, at higher energies, one has to include the effect of higher angular momenta to compute the full total cross-section. But this shows only the S-wave contribution. So there have been quite a number of studies by us from Franco's group, some of them jointly with Alex on isotopes of the F plus H2 reaction, as well as on other systems. But most of these reactions involve energy barrier. They occur through tunneling at low temperatures. But there have not been any studies of atom-to-atom exchange reactions that are non-alkali metal systems and that do not involve an energy barrier. And based on some results on the alkali systems, such a reaction should proceed by a very large rate constant at low temperatures. So that is what we are actually currently trying to look at, to study complex forming reactions which do not involve any energy barrier. But it is also a lot more challenging because of the large number of rotational vibration levels that one has to include in the calculations. So obviously there are some vested interest in looking at a system such as the O plus OH because it is of interest in mesospheric OH chemistry, where OH is a catalytic destroyer of ozone. So the density of OH in the mesosphere is partly related to the rate constant of that reaction. There is quite a bit of interest in astrophysical environments related to the formation of molecular oxygen and the oxygen chemistry. And I will show you there is quite a bit of uncertainty in the magnitude of the rate constant for the reaction at low temperatures. There are uncertainties in the measurements, uncertainties in the calculations. And it is also quite interesting from the cold collision point of view because OH has been cooled and trapped by the Stark deceleration methods. Maybe there are progress being made using the buffer gas cooling method. And so it would be, in fact, I guess, an interesting case for cold chemistry as well. And so jointly with Brian Kendrick at Los Alamos National Lab, we started, we began to look at this reaction, and as a starting point of our studies on more complex barrierless chemical reactions. So there are really not any reliable experimental data on this reaction for temperatures below 40 Kelvin, and it is also like due to the strong dipole-quadrupole interaction between oxygen and the OH, the long-range interaction potential is quite important in this system. And obviously, Alex has already identified, along with the others, some of the key reactions of interest in shock-heated gases that involve oxygen and hydrogen. So here, so the O plus OH and the H plus O2. So we are looking at the reactions from both sides. And earlier we have done some calculations on the reverse process, the O plus H2, mostly from atmospheric chemistry interest. So this is the method that we are using is a hyperspherical coordinate method based on the formalism developed by Russ Pack and Parker. It is called the adiabatically adjusting principal axis hyperspherical chord, or abbreviated as the APH. So what is shown here is the adiabatic energies as a function of the hyperradius. The O plus OH would be this side, and as it comes in, you can see, there is really no energy barrier, and this deep HO2 complex is formed. And as a result, there are like thousands of rotational vibration levels one has to include. This is just for the total J equals 0, and asymptotically, it corresponds to various vibrational energy levels of the molecule. And again, due to this large number of bound states of the bound or quasi-bound states of the HO2 species, the reaction involves or leads to very narrow resonances. So again, we are using potential electronically adiabatic potential surfaces calculated by the chemists. There are two potentials that we used. Again, these are very preliminary calculations, ongoing work. One is the DIM-KP. DIM stands for diatomics in molecules. KP stands for Kendrick and Pack. That potential, we believe it is a more accurate potential, at least in the low energy regime, because it includes the right long-range forces. But the other one used more widely in the chemistry community is the XXZLG, which is the the initial of the 5 authors involved in that work. So here I show, I don't know if you can distinguish the colors clearly. The red curve is the result of these authors. They used actually a very similar hyperspherical coordinate formalism developed by Jean-Michel Launay. And in fact, I think these are the only 2 codes which can really very well handle complex forming reactions. And so the black curve is our results on this XXZLG potential surface. And you can see they are essentially on top of each other, so the agreement is quite good. This is a result on the other potential, the diatomic and molecular potential. And due to the differences in the interaction potentials, obviously the results are different. And that also shows you the challenge, like how difficult it is to quantitatively or to quantitatively calculate potential energy surfaces for these systems. So anyway, we are quite pleased that the calculations reproduce, from both codes produce nearly identical results. Now, to calculate rate constants, of course, one has to do calculations of reaction probabilities for all the angular momentum partial waves that contribute, and that is for high angular momenta, it is almost impossible for this reaction, and that is also why this is one of the very, very few reactions that the chemical physics community is still not able to handle in terms of computing accurate rate constant without any dynamics approximation. So most calculations have used some sort of approximation, and the one that is widely used is what is called a J-shifting method, in which you calculate accurately the results for total angular momentum J equal to 0, and then use an approximation called J-shifting, through which you get results for higher angular momenta, which is actually not a very good approximation for this system because it doesn't have an energy barrier, and the J-shifting method is more suitable for reaction with energy barriers. So anyway, the most interesting thing I want to point out here is that the red curve is our result on this XXZLG, and the green curve is the result of the Zhu et al., which was obtained by using the results of the red curve here. In fact, that means we should get identical results because they seem to be on top of each other. But for the rate constant, we see some big differences, and we almost spent 2 months to figure out exactly what was going on. So I'll explain it in the next slide. And the blue one is our result on the DIMKP. So again, you see that there are in this temperature range, the difference is not dramatic, but there are differences. These are a sample of experimental data, including some NASA recommended values. And these two data points are the most recent experimental data from the group of Carty et al., that is the group of IWM Smith. So this is 39 Kelvin, this is 120 Kelvin, seems to be, the rate constant seems to be almost independent of temperature, but that is not what this green curve shows. It shows a very rapid decrease in the rate constant with a decrease in temperature, and so at 10 Kelvin, the value here is about nearly 80 times smaller than the value here. So that was a dramatic drop in the rate constant, and it appears that it is very sensitive when you have reaction probabilities or cross sections, and when you want to compute rate constant, you need to integrate it over a Boltzmann distribution of collision energies. And if that is not done accurately, and if you don't include the threshold region in the integration process, and if you don't have enough resolution in the energy dependence of the reaction probability, then a lot of things can go wrong, and so I believe so that's what we found. These various curves are our calculations, but which uses different degrees of energy resolution in computing the reaction probability. So there are the set 1, set 2, set 3 corresponds to increasing degrees of energy resolution, and the set 4 is the set 3 plus this low energy regime, which actually makes an important contribution for this DIMKP potential, which has the more extended long-range description, but it doesn't actually make a big difference for the other potential. You can see the blue one and the dark curve is essentially on top of each other. So this makes about a factor of 4 difference, and then if you don't include the threshold region, then of course most of the rate constant will decrease substantially, and we believe that was the main source of the substantially smaller value of reaction rate constant calculated by the other authors. So anyway, so this is work in progress. We have submitted a manuscript as a communication to JCP, which is still being reviewed, but there was one of the referees asked precisely, well, if you are using the same methods, then why is that that we get a very different result from at low temperatures compared to the other ones. So that is how we ended up looking at these things, and hope we will hear from the journal soon. Okay. So the other thing that we are, how many? 3 minutes? Oh, yeah, I think that's enough. So I briefly want to discuss some ongoing work on molecule-molecule collisions, which also is important in ultracold traps when you have high densities of molecules. Molecule-molecule collisions are also of interest in astrophysical environments, especially in H2-dominated regions. And there have been some, quite a bit of studies of rotational excitations in H2-H2 collisions, but there aren't that many calculations of raw vibrational transitions in H2-H2 collisions at temperatures of interest in astrophysical environments. So jointly with Roman, we have been working on developing a full-dimensional quantum scattering code to treat diatom-diatom collisions. And so now we have a code that is jointly developed with Roman Krems on H2-H2 system, which Roman likes to call 2BC. And so I will show you some illustrative results. And again, the approach is based on the Dalgarno formalism, which is an extension of his method he developed for rigid order collisions by including vibrational degrees of freedom of both molecules. So again, these kind of calculations are most conveniently done using the Dalgarno formalism. So what I want to highlight here is some interesting results. We have three initial states for the H2-H2 system. In one case, in all three cases, I have one molecule in vibrationally excited. In the other case, vibrationally ground state, but the rotational levels are different in the three cases. And these initial states are labeled as 1, 0, 0, 0. These numbers corresponds to the vibrational rotational quantum numbers of both molecules. So the elastic cross-section is almost insensitive to the initial states shown here, but the inelastic vibrational relaxation cross-section is quite sensitive to the initial state. It is quite low in the first case. It is somewhat intermediate for the case where you have the molecule is rotationally excited, and it is much larger for the case where you have one molecule vibrationally excited and the other molecule rotationally excited. And so such a dramatic difference in vibrational relaxation cross-section was initially puzzling, but it turns out that in molecule-molecule collisions, it is dictated by two factors. One is the conservation of internal energy. That is, if the internal combined vibrational and rotational energy is the same before and after the collision, so we have a near resonant process. And if the internal rotational angular momentum, sum of the rotational angular momenta of the two molecules, is also conserved during the collision, then becomes a highly efficient near resonant process, and exactly that is what's happening here. We have the initial state is 1, 0, 0, 2, but after collision it goes to 1, 2, 0, 0, and what is plotted is cross-section as a function of what we call the combined molecular state, where the internal energy increases in this direction. So you can see the energy gap between the two states is very small, and it's about 25 Kelvin. So it is not exactly resonant, but it is near resonant. But that condition is not satisfied. Here, you can see the most possible the initial state is 1, 2, 0, 0, but the most probable final state is 1, 0, 0, 0. So that corresponds to a pure rotational transition. And in this case, this is the initial state. So this corresponds to the elastic scattering, but there is no preferred final state in that. So we don't have this near resonant process. And finally, the near resonance process is also maintained, or it is also present when you have vibrationally excited molecule. So here is so three types of initial conditions: V0, V prime 0, V2, V prime 0, V0, V prime 2. These are the initial rotational and vibrational combinations of the two molecules. And when the near resonance process is present, the cross-sections are very large, and these cross-sections are calculated at a collision energy of a microkelvin. So again, this is a work in progress, and and some conclusions from this study. So I think we are at a time where exciting developments are taking place in both in theory and experiments. Roman has shown how these collisions can be controlled using electric and magnetic field, and some of the calculations I showed here that in chemical reactions one may have large rate coefficient for barrierless reactions, and also for the case of molecule-molecule collisions, one can have interesting near-resonant transitions. So I like to thank my collaborators. Some of them are listed here, and except Brian and my postdocs, Gulwin and Philip, all of them are here. Well, thanks once again for the opportunity to talk about some of the things we are doing, and once again, happy birthday, Alex.
Now the paper is open for discussions. Any question? No question? One question.
So on these inelastic collisions that you discussed at the end, what are the chances of being able to extend to more complicated atoms? Say lithium or sodium collisions rather than hydrogen?
The molecule or the or collision between, say, two lithium dimers. I guess we may be able to do for S waves. The limiting factor is essentially the number of rotational vibration levels that we have to include in the calculation if you want to get some accurate converged cross sections. But if you have, suppose there are some near-resonant process such as the one that I just identified, then the calculation, the cross-section between those near-resonant levels will be so dominant that transition between all other levels will be not very important. So of course, only if we do the calculations we will know, but if we have such process occurring, then we will be able to do the calculations. Because then we don't need to include all other channels in the calculations. But the question is, unless you do the calculation, it is difficult to know whether such a process would exist or not.
If you're asking if the calculation like this would be, how easy is it to do? And I think the answer to that is that with the current technologies, it would be impossible, primarily because, when it comes to alkali metal dimers, these collisions involve chemical reactions. Like when we have two lithium dimers colliding, they're going to exchange atoms, unlike in collisions of H2 molecules. So these are barrierless chemical reactions, and you have, if you want to do a rigorous calculation, you have to include the reactive channels, and for a four-body collision problem, that's impossible.
People have done at higher temperatures, but doing it for low temperatures where you have to integrate these equations to hundreds of atomic units becomes...
May I ask as a comment that in the group of Jean-Michel Launay, they are doing such calculations?
Atom to atom, not atom to atom.
Okay. Let's start by atom by atom. Any other question?
What are the prospects for extending these near-resonant calculations to cases of higher J? So particularly interested in transfer from vibrational excitation to rotation.
I think that is where we are heading to some of this, the H2H2. We certainly want to look at the excited vibration levels and rotation levels, and that prospect is actually quite bright that we will be doing it in the next year or two. And essentially, it is a computational problem now that we have the code working, and so the prospect is actually quite bright.